This session is with Sayan from IIT Kharagpur, and we will talk about Born-Infeld gravity.
Okay, so let me thank Pamitavo and everyone else for inviting me. Normally, as it's been said, that FTAG used to be a meeting where everybody spoke on the board, but I do it every day, so maybe I get relaxed. Okay, so let me just tell you why I chose this topic. That is important, and it goes very well, according to me, with the title of the meeting. As you will see, that this is some work which was started by Eddington, and he rewrote the Einstein answer in a different way, and that was sort of used by Born-Infeld. They admitted it in their paper, and that led to Born-Infeld electrodynamics. And then later on, many years later, Dazer and Gibbons first asked the question whether you could have a gravity theory based on the idea of Born-Infeld electrodynamics. So that's how it's a field theory which kind of inspired a gravity theory, and therefore you could say it's sort of directly related to the main theme of this meeting. So what I'll do in this talk, I'll just basically tell you about the theory and give one or two examples, and in the next talk, which one of my collaborators and student will give, he will tell us about some of the solutions that we have obtained and some of the other results that we have. Okay. So that's the plan. So let me move forward from here. And of course you will immediately tell me, well, here there is yet another theory of gravity. And there are so many theories. You can see this huge list that I have given, and there are many more. And last year when I was preparing this talk, incidentally I have given this talk in Sayan Institute, and there was a Pathomitra who was there, so he knows most of the talk, so he can sleep a few words. So about there are 30 theories now running for survival, and each theory has its own plus and minus points. But every theory is useful because they teach us something. How do I go up, down in this side? Yeah. Okay. Every theory is useful because they teach us how good or bad GR is today. So we are not biased as such. We would like to look at all the theories that we have in mind. So this was last year when I prepared this talk. I looked at 30 theories. And last Saturday when I was rewriting parts of this talk, I found this diagram in one paper. Okay. And this is, Tessa Baker is not a theory of course, but this is the person who has made the figure, and this is in this article. It's a nice article, it's called Beyond Lambda CDM. It's a conference summary, and it addresses all the basic questions that are asked in cosmology from a modified gravity perspective. So there is modified gravity, and you can see there are so many theories over here.
I don't find massive gravity.
Wait, massive gravity is also. Here it is. So, and I counted this last Saturday, and I found there are 34 of them. So you see what I said in the last slide is also something which is over here, and there is something for everyone in this room, I guess. And I can pick out every person and attach a theory to this.
How do you tell a theory is better than another?
Sorry?
What is the criterion of evaluation?
Now, I am no one to tell you about which is better or which is worse. I think observations is the only test by which you can finally. There are no observations for quantum theories of gravity. These are all classical theories of gravity as such. Some of them are quantum inspired, but what I am talking about is, and what I will be talking about throughout, is a classical theory of gravity. Okay, so that's the diagram for modified gravity. Naresh is here. You should take a look where he falls in. He falls in here. Love gravity.
He falls.
And this is where I am, EBI, you can see a small little bit, and there are lots of others.
What is that EPA?
Which one?
EI?
EBI, Eddington Born-Infeld.
Oh.
There is also KGB, by the way. Okay, so let me go ahead now. Let me move to the main thing, and let me tell you that there are two aspects which are very important over here, and one is the square root and one is the determinant. Okay, So the whole of the talk is based on these two things, that the square root and the determinant, and the place where the square root and the determinant occurs most naturally is the volume element. Okay, so root g d4x. Okay, so that's the starting point, and this is something which Eddington wrote about in his book on 1924 on relativity. And as you know, Eddington was the person who knew relativity at that time. And Schrödinger also mentions it in 1947. So this is the standard Einstein-Hilbert action with c equal to 1 and 8 pi g equal to 1. And Eddington wrote down this over here, and he called this a generalized volume, which is in section 101 of its mathematical theory of relativity. Why he wrote it is there in his book. Something came to his mind and he wrote this out, and he wrote this, and he had a constant over here, which of course has been added later on. He wrote this generalized volume. You can see it's a determinant of Rij, which is over here. We actually don't know whether it's a minus sign or plus sign, because we don't know what is the determinant of Rij, but suppose it is minus, then you have to have a minus. If it's plus, then you have to have a plus. Okay. So now how do you show equivalence? Once you write it down, you will realize that if you want to show equivalence, you can do it only in something that we have been discussing since morning, that is de Sitter space. Okay. So once again, this talk also has a connection with de Sitter space. So what you do is you take this equation, Rij equal to lambda Gij, you invert it. You calculate the determinant, plug it in over here, and you will get this action. You can get a relation between these two actions for de Sitter space and not for anything else. But you have to notice what is important is that here you have a C and a G in this general relativity. But now what I am doing is I am putting
Sign of lambda is not used, right?
no,
This equals.
no, sign of lambda is not.
So anti-de Sitter also will work.
Yeah. So I have another constant in a classical theory. So this is the crux of the whole issue. Apart from G and C, I have a third constant which is kappa, and which I plug in by hand over here, and I want to see what this is going to do, what changes it is going to induce in my way of looking at things. So kappa has dimensions inverse to that of lambda. Okay, so this is clear, so let me move ahead. I have this action which is different from Einstein-Hilbert action. What I am saying is that this action is valid only for de Sitter space because of this little bit of logic that I showed you. And then I move ahead and I realize that this action over here automatically implies a connection formulation, okay, without reference to a metric. So you can think of this in terms of a connection formulation.
What happens in flat space? Flat space?
It's valid only in de Sitter space. Flat space will go to 0. Everything lambda is 0, so everything is 0.
So this is a very particular.
It is very particular. We make it more
also
general.
to the choice of the metric in de Sitter space. Because in
Of
local
course.
regions
Yes, of course. Yeah. So, but this is very specific, and this is something which Eddington just said for de Sitter space and nothing else. Okay. So, if you vary this with respect to the connection, you will see why de Sitter space comes in from here. You will get something like this. Okay. And you can write this as a solution in terms of a metric, which is over here. So your field equations become like this, and that implies de Sitter space provided you identify Qij with Gx. Okay, and lambda with 1 over kappa. So that's the story. And in the connection form, you have this field equation. R up Ij is the inverse of the matrix representing the Ricci tensor R down Ij. Remember, this is a connection formulation, there is no metric. So you don't know how to raise it up and down. So you have to define what is Rij up, and that's the inverse of the matrix that you have. So you rewrite as Einstein equation by equating Qij equal to Gij and kappa equal to 1 over lambda. But you find something interesting. You see that S Einstein-Hilbert is actually proportional to lambda, whereas S Eddington is proportional to 1 over lambda. So you ask the question whether these are different regimes, and this is of course restricted to de Sitter space-time only. And the main trouble is that how do you couple matter? Okay, so that's the main trouble, and that trouble has to be addressed. And therefore you must be able to move away from de Sitter space and to something else more general where you can address the issue of matter properties. Okay, so let's see what Born-Infeld wrote in 1934. if you look at that paper, page 425, in this paper they write, specially some of Eddington's formula developed in section 101 of his book have a remarkable formal analogy to those of this paper in spite of the entirely different physical equipment. Okay, so they do acknowledge whatever Eddington did. Born-Infeld referred to an analogy. What is that analogy? The analogy is, with Eddington's ideas, is in the sense of a determinant and a square root. So these are the two things which I mentioned right at the beginning. That's the basic thing in this talk, that there is the idea of a determinant and there is the square root, and these two things are important throughout the text. So what is the goal of Born-Infeld? All of us know that self-energy problem, singular electric field at the source location, and it's cured. And you have the Born-Infeld electrodynamics action, and once again you have the square root and the determinant. This is all well known.
Sayan, usually the root minus d, the square root is motivated by demanding the volume element to
Is invariant. Here there is no such motivation. He didn't have any such
No, but he
motivation.
called it a generalized volume.
He called it a generalized volume, but see, the point is that if you want to think in terms of it being diffeomorphism invariant, you have to define that kappa det Rij in terms of a metric.
No, but here he presumably only took it only dimensionally.
You don't need dimension. Yeah.
Dimensionally,
Yeah,
so
exactly.
the volumes
Yeah.
which require a square
Yes,
root.
yes. And therefore you need an additional constant.
Constant to-
That constant comes in, and that's why
Yeah.
you have this new constant apart from G and C.
Correct.
So that same kind of a constant also appears in Born-Infeld. If you look at Born-Infeld, you will find that electrodynamics has only one constant, C, but now Born-Infeld has got two constants, C and a new constant, B. And that is what I refer to as kappa. So this is your Born-Infeld electrodynamics action, and the field equations when solved for a point source lead to a resolution of the self-energy singularity in the electric field. That is well-known stuff. Kappa plays the role of a new parameter which yields an upper bound on the electric field of a point charge. The theory is nonlinear, it's not like Maxwell, and there are various avatars of Born-Infeld. One of them is scalar Born-Infeld, which is actually the tachyon matter that string theorists would like to talk about. That's the same thing, and that has an action which is given by this. Capital T is a scalar field, there is a potential over here, and that's the usual action for the tachyon condensate in string theory. Okay, so now let me move away from the square root and this term. Let me go back to very early work by Hisham, Salam and Stadi in 1971, where they talked about something called F dominance of gravity. That's the title of the paper. Okay, and they drew their motivation from the rho gamma model of hadron electrodynamics, which is a spin 1 model. Hadronic electrodynamics can, to a good approximation, be separated from lepton electrodynamics. There is a direct interaction of the photon, which is AIGI lepton, but an indirect rho gamma interaction, which is given by this. And you have a Lagrangian, which is the sum of 3 terms, and you can use field of 3 definitions to generate a mass term. So that was rho gamma electrodynamics. This was not, of course, Hisham Salam Studies work. What they did was to extend it to spin 2. Okay, and they talked about a graviton and an F meson, both spin 2, and I wrote a Lagrangian which is like this, but remarkably they assumed LF and Mg to be the Einstein-Hilbert actions, and they put in a coupling over here, a mixing term which is a term which creates a mass for the F meson. So that was the total action. So now you have two metrics. So that's the whole idea. You have two metrics, F and G. And they said that in far regions from hadronic matter, G dominates, inside hadrons, F dominates. And if you look at geodesics of F, and you can ask the question whether F-mediated gravity can be repulsive at short distances, and so on and so forth. So there are various questions they ask. The reason why I am telling you all this, you will realize in a moment, that the fact that there are two metrics over here, F and G, is basically why this is by and large the first example of a bimetric theory after what Rosen did in 1940, which is not something which is talked about today, but this 1971 work is an example of a bimetric theory which is quite fashionable nowadays, and there's a lot of work on bimetric theories.
Sayan,
matching
in
gravity.
action,
Yes.
when you have to include a root minus g d4x,
Yes.
that root minus g, does it come from g or f?
Where, which action?
for the full action. This is the
This
Lagrangian
action.
density, LF plus LG.
Okay.
But in the action there has to be a...
Yeah, so in
volume
this it will be root minus f, in this will be root minus g.
And then the other case?
The other one, it is, you have your choice. Well, it's a coupling term. G and F is coupled there. So you can choose G, you can choose F. There are various kinds of models which
And
people have
F,
discussed.
does it also universally coupled to other matter like G?
This F part is separate, G part is separate.
No,
Completely.
for other matter field. In order that...
Oh, you are saying that if it's no. This model doesn't have any other matter aspect. It's only F and G, and you just work with that. There are generalizations with other matter field terms.
Space term related to which?
G is baseline, F is the
So
F
it's
is
not diffeomorphism in way.
So this whole thing is that in biometric theories you have two diffeomorphisms. One is F diffeomorphism, G diffeomorphism. You think in that way. So that is the idea. All biometric theories have that.
No, but that interaction term will have no
Interaction term is something mixed up.
Also doesn't have.
It's very mixed up.
Badly mixed up. Anyway, the main purpose to tell you about this is that there are two metrics F and G. That's all. Okay, so let's move ahead. Let's come to 1998, where Dazer and Gibbons, they asked this question, that is there a gravitational analog of Born-Infeld electrodynamics? And they wrote down an action which is like this. You can see there is a C capital Xij, where Xij are terms quadratic or higher in curvature. Okay. And they did a metric variation, and they obtained the field equations. And later on with the same action, Wollich did a Palatini variation of the Dazer-Gibbons action without T capital Xij. So that's how it all started. That's the question related to Born-Infeld electrodynamics. How do you construct a gravitational analog of Born-Infeld electrodynamics? The idea is essentially to see something similar to what you see in Born-Infeld electrodynamics, some kind of a resolution of a singularity. Whether that thing happens over here, that is the question. Okay. And we will see that happens in the modern version, the most recent version of Born-Infeld electrodynamics. And that's the theory of due to Max Bernados and Pedro Ferreira, which they wrote down in 2010, which I'll come to in a moment. Okay, so let me go to Wollich. Dan Wollich writes down an action like this. Inspired by Born-Infeld electrodynamics, he puts in the matter contribution over here and makes a mess of the whole thing. So it becomes horribly complicated. And this he writes as Mij equal to del I phi del j phi, and he allows a non-symmetric connection, so he gets all kinds of things in the theory, and he's unable to solve it in very many situations. But one conclusion of his is that point charges are not allowed; they must have finite size. So that is something which he concludes. Okay. So let me now move on to matter couplings. Let me tell you some early work by Ferraris and Pijoski in 1981 and Laplos in 2009. So they started the Palatini gravitational action, I, G, gamma, psi, no metric derivatives. So you can express Gij in terms of gamma and psi. You put it back in the equation of motion, not possible for the massless free boson, and replace this formula back in the action to get a purely affine action. And that is exactly what Eddington and Einstein did, Einstein did. The same thing they did in a more genuine context. But the main thing is that you would like to know a much easier way of coupling matter. That is the idea. Now how do you do it? And that is what was the most obvious way, but somehow people didn't talk about. Okay. So you move away from trying for a purely affine formulation or for a GI equivalent formulation, and that's what they did. What did they do? They did something absolutely trivial. Okay. You just add SMG psi that you do in usual general relativity, and you go ahead and do it. Go do the variation and see what happens. Okay. So instead of putting in the matter over here, you put in an extra matter term, but you say you have a G metric and the psi are the matter fields, and that's how you write down your SPF. Okay, this is the work of Bernados and Ferreira in 2010. Lambda, capital lambda is small lambda minus 1 by kappa. There is a constant over here. It is related to the cosmological constant and the kappa. And this means determinant and so on. So small lambda must be non-zero, otherwise metric variation with no matter is meaningless. And this is the introduction of matter is conventional, unlike what Wollich did. Okay.
But this is not a purely connection formula.
No, it's not a pure. It's a formulation which is they do Palatini variation. So it's a Palatini variation which is used. Okay. So what are the limits? You will see that if kappa r is small, r means Rij, you get the Einstein-Hilbert action. Kappa r large, you get Eddington action. So these are the two limits. With matter, it's not equivalent to Gr. Okay, but without matter, that is the important thing about this theory, that without matter, everything in Gr works. There is no change. Okay, it's only inside matter that you have differences. So if you vary this action with respect to gamma, you get this. Qij equal to Gij plus kappa Rij. You say that Qij is a metric with a connection. Okay, and that is important because otherwise you would not be able to show that this is Q and G different variables. That is crucial over here. So you have to define a metric Qij. But remember, this Rij is a function of Q's. Okay, so this is Rij_Q. So if you vary this once again with respect to Gij, you get another equation which is like this. So these are your two field equations. Okay, so now what is the problem? So let us go back. You have vacuum solutions in Gr and this theory are the same. The vacuum theory is equivalent to Gr. You can check usual conservation derivative using Gij, del J Tij equal to 0. That holds. One can consider the EIBI action as a bimetric action. That's why I talked about bimetric, F dominance of gravity and so on. And where the two metrics are Qij and Gij. Gij is the physical metric, Qij is the auxiliary metric. Okay. And therefore, in summary, what you have is EIBI gravity, Eddington-inspired Born-Infeld gravity, implies three features: determinant, Born-Infeld, and bimetric. All these three things together combine in this construction of the theory. Okay, so let me summarize once again. Dazer-Gibbons did this, metric variation. Volek did this, Palatini variation. Vanados-Ferreira wrote down this over here, simple matter coupling, and did the Palatini variation. Okay. So we will work with this theory and show some examples of what happens if I work with this theory. Okay. So let me first do an expansion in kappa. So kappa is a parameter. Expanding the field equations to second order in kappa gives you something like this. This is over here. This is Sij, which is a product of T's, Tij. And this correction term is traceless. Correction term quadratic in Tij. Now those of you who have worked in brain world gravity would say that, well, you are getting something very, very similar. There you also have this Sij which was like this. So that is the effective Shiromizu, Maeda, Sasaki equations on the brain. Exactly the same thing. Why are you getting this? Well, that's a question that's one of the open questions. But my own guess is that when you write the action, you have two terms. One is Q and one is G. And these two terms, one of them is heavily coupled to the other. But these two terms, if you recall, are basically terms which are brain actions. Okay, they are the induced metrics on the brain, you would say. If you think bring in the brain, then they are like induced metrics on the brain. And there is a coupling between the two induced metrics. And that probably is giving rise eventually to something like this. But that hasn't been worked out. That's just a guess.
But here the Q and G both refer to the brain. There is no bulk.
No, you don't know. One has to construct it. You can have two brains over here, one with Q and one with G. One can try to see whether there is an interplay between the metrics, there is an interaction. Okay, so all that has to be worked out. And this is not something, but there is a similarity which is important, and that is what we notice. But then there are more terms of order kappa which are problematic, and we'll see how they are problematic. Okay, so if you want to solve the field equations, the variation with respect to Gij gives you this. So if you are given a Tij, one obtains 10 algebraic relations between the components of Qij, Gij and Qij. Okay. And variation with respect to gamma gives you another equation, which is this. Qij is another metric, Q and G diffeomorphisms. So there are 20 equations for 20 variables, but what is the big problem? The big problem is that you don't know how to invert this. Okay. That is where the problem is, and that is where constructing solutions becomes very, very difficult. If you were able to invert this, that is, see, Rij are functions with Q's. This is for Q's, and this is Qij equal to Gij plus kappa Rij. So you can't invert it. Because you cannot invert it, it becomes difficult. And Therefore, you have to make an ansatz for Qij and Gij and then work with the ansatz and find out those functions for specific cases. Okay. So what is the Newtonian limit? So that's the immediate question you ask. You have constructed a theory of gravity, you want to know what is the Newtonian limit. So there is, you take ds square as this, with a phi and a phi q, you substitute in your field equations. This is your Poisson equation. The new Poisson equation is this. What is the new thing you have? You have this term which is del square rho. Okay. So there is a term which involves the derivative of the matter densities. Okay. And this term depends on this new constant kappa. But you will see later on that having a derivative of the matter density is a problem. Where is it a problem? It's a problem when you want to have two regions with two different matter densities and you want to connect them up. There you have to use junction conditions. And there you have a problem if you have a derivative term of the matter densities. So for stars, for instance, it's a problem. But for the universe as such, it's not a problem. Okay, if you take the coarse-grained universe models, then there is no problem. So the Newtonian limit gives you something new, and because it gives you something new, immediately the first thing which people tried to do was to try to fit galaxy rotation curves. Okay, and it does fit. People have done some work where they try to say that this could be a basis of understanding the galaxy rotation curves and things like that. If you want to look at the next step, that is the static spherosymmetric solution, so you write your metric, which is this, and this is Schwarzschild de Sitter. You have a complicated thing over here for FR Sayan. You have the ER where the singularity is resolved, but in general this is a singular metric. There is no removal of singularity as it was expected. Okay, because of the Born-Infeld nature of the
So what is the variable q there?
which is
R2 R4 plus 2 kappa q square.
Q is the
Minus
charge. It's a charge.
Charge. Not related.
This is with
to
EM fields. This is with EM fields. So it's like it's the generalization of Reisner-Nordstrom solution. This is no sources, you have this. Okay. So observe that for kappa greater than 0, electric field regularized for r equal to 0. The metric functions are singular at r equal to 0 and these points. Okay. So now let me move to cosmology. So this is the interesting part.
Can it have a rational Nordstrom as a limit?
Yeah, it does. It does. We have checked that. It does have a Reisner. So if you want to do cosmology, then once again, as I said, you start with the metric ansatz for the G metric. That's the first line. You have another metric ansatz for the Q metric, which is the second line. So now you can ask me, why did you choose UT over here? Why did you choose VT over here? This is basically some choice you have to make. There is no other way, because as I said, you cannot invert those equations. So if you make these choices, your equations become simpler to handle. There is no rationale behind making these choices as such. Okay. So UT, VT and AT are the three unknowns. You choose a perfect fluid energy momentum tensor.
Essentially you have two unknowns. Because UT you can observe in T.
Yeah, but you keep it at the moment. As you will see, UT from the other equation will give you something related to the densities and pressures. Okay. So energy momentum tensor is assumed like this, and the 0, 0 and 1, 1 components of this equation will give you UT and VT in terms of rho T and PT. Okay. PT and rho T are basically things which include the cosmological constant lambda. Okay. So overall 5 unknowns are over here, and you want to solve it. So if you solve it, you can get the Friedmann equation finally, which is this. That's A dot by A whole square, and this is what it looks like. So this is the Friedmann equation for this theory. Okay, lots of unknown, lots of complicated functions. P over here is like this, so it's a horrendous thing, and you want to find out what is the metric, you have to use numerics to figure out what exactly is the metric. Okay, or what is the scale factor.
T is the trace, isn't it?
No, it's not the trace. It's just P plus lambda and rho minus lambda. That's all. So this is rho T plus PT. The kappa is sitting over here everywhere. And if you, for P equal to rho by 3, lambda equal to 0, you get this equation. So for small rho bar, if you look at this, if you take the small rho bar limit, you will find h squared equal to rho by 3. It's very easy to check that. Okay. Note that h square has zeros at rho bar equal to 3 and rho bar equal to 0 for kappa greater than 0. So this is a crucial point. Okay, this actually tells you that it's possible to get a lower bound on the value, on the minimum value of the scale factor. Okay, and therefore you can remove the singularity, and that is done exactly in the same way as you would expect for a Born-Infeld type theory to do it, through the introduction of the third constant which I put in by hand apart from G and C, which is kappa. Okay. So for kappa less than 0, the zeros are different, and note the difference with the usual FRW model where 3h square is equal to rho and the 0 is at rho equal to 0. So that's a picture. H square versus rho. You plot it and you find that there are two zeros. Here you find that they are at the same point. They are not at the same point because rho b is defined in different manner for the two curves. Okay, so they are at different points, but you have made them, the plot is such that you have made them coincide at the same point. But you see the main point is that there are two zeros for rho as a function, h square as a function of rho. Unlike the usual Friedmann equation where there is only one zero for h square as a function of rho. What are the solutions? So these are the solutions for kappa less than 0 and kappa greater than 0. So this is one solution for kappa less than 0, this is the solution for kappa greater than 0. So they are numerically obtained, but they have a minimum length, that's the crucial point. And the top one shows a bounce over here, the bottom one approaches the minimum length at t going to minus infinity.
So just remind me, what is the kappa?
Kappa is a constant in the Born-Infeld.
It's a coupling.
It's that you have that 1 over kappa square root of gij plus kappa rij, that kappa.
And you write me both the kappa, positive, negative,
Both are allowed at the moment. You can think of doing solutions with both.
But in energy, in particle physics units, kappa as 1 over m to the power 4 dimension.
No, I'm not talking about any particle physics.
No, 1 over m to the power 4 dimension. The kappa is not dimensionless.
Here it is not dimensionless. Here it is not dimensionless.
Correct. So it is having a dimension.
It has a dimension. Yeah.
1 over
Length
energy to the power 4.
In g equal to c equal to 1 unit is 1 over length square. Length square, sorry, not 1 over length square, length square.
Length square.
1 over kappa is 1 over length. Okay, so there is no singularity, and that is what was the main point in the paper by Vanados and Ferreira in 2010, which led to attention on this work and this theory. Okay, and since then there has been a lot of work on this. There are various other scenarios which people have looked at. For instance, pressureless Newtonian stars. You have a Poisson equation which is this. You write down your hydrostatic equilibrium equations. P equal to 0, kappa greater than 0 has a solution. So that is something strange and new. You can find rho r, you can find omega, and you can show that it is stable against radial perturbations. Okay, P equal to 0, Newtonian star for kappa greater than 0.
Is this metric asymptotically flat?
Which metric?
Is metric Benjamin's
Metric. I have shown only one metric, which is the cosmological metric. That is certainly
FRW is asymptotically flat.
not. FRW is not asymptotically.
No.
FRW is not asymptotic.
No, not. I agree. So what
The other ones are. Earlier one, the spherically symmetric one, is asymptotic.
what I am trying to understand is, do these fulfill the energy conditions?
Yeah, that one is to check. But whatever we have taken P equal to rho by 3, they do fulfill.
Because the removal of the singularity
Yeah.
typically happens when you remove the energy conditions.
Yeah, but there is no such theorem as such. But both ways it can happen.
Can, but I don't know the example.
That is the point what I'm saying. No, but you see, sorry, the one question is here, those all statements are so long as you are within general relativity. Here you are.
Here it is not
You are
general.
extending-
No, but anyway, in general, one would say that there is some kind of a, if you violate energy conditions, you can have non-singular
No,
states.
but-
That is the correct, that is the thing that you are saying.
But
That's what I am familiar with. I don't
Yeah.
know any theory.
But there are counter examples also which says that it need not.
Yeah. No, but Sayan, here, one other thing, one more intuitive level, what you have is, you have a pressureless fluid in hydrostatic equilibrium, which means there is something which you are thrown in here,
Which is doing the job.
which is doing the job, which
Exactly.
is counteracting the gravitational
Exactly,
attraction.
exactly. Yeah.
And-
This is what you have thrown in here.
But So that means, that's where you're saying, that is effectively you have thrown in a repulsive thing to
Exactly.
counteract that.
Exactly.
And the Ball's question is, the energy condition corresponding to that should be violating that. Because
Maybe it is
effectively, if you want to define an effective energy condition,
yeah.
there should be some violation, otherwise you want.
Yeah, the problem in this is that energy condition by itself is difficult because there are two metrics involved which are really coupled to each other.
That's right.
So,
But if I want to look, it's analog in the my usual sense,
somewhere
I try to find an energy condition which
Yeah.
will be.
no, that is there. I'll come to that in a moment.
Yes.
Later on. Let me just move on. So you can think of polytropes in a similar fashion, where this is your equation of state, and this is also stable. For kappa greater than 0, unstable for kappa less than 0. That is the rho and the omega and kappa and so on. Okay, people have studied gravitational collapse also. Collapse of incoherent dust has been studied. When kappa less than 0 collapse does occur, but when kappa greater than 0 collapse can be violated. Matter fields show an oscillatory behavior whose period depends on kappa eta. Eta is a solution parameter. And singularity formation can be avoided, but these are all case specific studies. It's not something which is general you can state, like in general relativity also. Okay.
But does collapse give rise to the horizon?
Which one?
No, when you consider gravitational collapse.
Yeah.
Collapse.
There are examples of horizon regular space times. I think there are some examples which we talk about in the next talk. Then there are brain noise models in 5 dimensions, cosmology, a lot of work has been done, constraints, phenomenological constraints, tensor instabilities, compact stars, solar system physics. So a large number of papers over the last 4 or 5 years on this theory which you can look up. But this is what is more interesting, is that Fernandez Ferreira has GR with apparent stress. So this is something which Delsarte and Steinhoff talked about in 2012. And this is what they wrote down. This is the Einstein-like equations of general relativity, where you have a Qij and a lambda delta Ij. And this is, but then this is for the Q metric. So that is the problem. This is for the Q metric, and once again the G's and Q's are badly mixed up. The tau over here is square root of G by Q, the determinant of G and determinant of Q. Okay. Singularity avoidance is signaled by the poles of this. This is what they showed. So this is a signature of a way to find out whether there will be a singularity or there will be no singularity. Okay. For instance, for a perfect fluid, you can see tau is given by this, and if you have p equal to 0, you have this. So a divergence of rho is signaled by a 0 in tau. So that is some quantity which you can calculate and see for specific cases whether there will be a singularity or not. Now this can happen only for kappa greater than 0. For kappa less than 0, it is possible that rho be bounded below but at a finite value where tau tends to infinity, that is near to 0. And one can verify this for perfect fluids with rho p not equal to 0. The main point over here is the fact that you could still write something which is like an Einstein theory. But then for the Q metric and some mixing. And there is a mixing, the gamma over here is defined like this and the tau is defined like this. So it is not something where you can completely decouple the Q and the G. The coupling is still there. Okay, so this is still not a success as such, that you are still not able to resolve the problem, that you have to learn of a way of solving that equation Qij equal to Gij plus Rij as a function of Q. You cannot invert it. So as I said earlier, there are problems because of the derivative terms, and this is the general derivative terms over here. And these terms are problematic mainly because if you want to deal with situations where you have a boundary separating two different energy momentum tenses, you have to look at junction conditions, and that is where these derivative terms create a problem. For stars, for instance, is a problem. There is a resolution by this guy in 2014, but this problem also appears in FR gravity, the same kind of problem, but it's still not completely resolved as such. So let me give you the final remarks. It's interesting, new and structurally different theory with a new constant which matches with GR in that form. That's statement number 1. Okay, it's structurally different from general relativity. And it has a new constant apart from capital G and capital C. It involves the determinant and the square root and the Born-Infeld structure, all three together. And has the potential of generating non-singular solutions in the classical theory. similar to Born-Infeld, where you have Born-Infeld electrodynamics. It is problematic because of too much reliance on numerics. Exact analytical solutions are difficult. You can ask, is kappa positive or negative? What is it? Nobody knows. There are various bounds from various scenarios. You can ask, is kappa can be treated as a field itself? Okay, so that is one possibility. Lots of uneasy questions exist and need to be understood, but not really a substitute of GR. Very unlikely to be so, but a good reference for future tests in strong gravity domain. And in the next talk, you will hear some of our work in 2+1 Einstein Born-Infeld gravity, where we have some exact analytical solutions. We have something on Lorentzian wormholes, which Rajibul Sheikh has done, where you can do away with energy condition violations in this theory. Then we try to look at Born-Infeld structures in Born-Infeld gravity and Born-Infeld electrodynamics together and see what happens in that case. There we have an exact analytical solution. We have done gravitational lensing calculations. There is a reduced Born-Infeld FT theory, where we have done cosmological solutions, we have done data fitting and all that. And recently we have been working on this scalar Born-Infeld matter with Born-Infeld gravity. We have some very nice analytical solutions, plus we have tried to fit. So that is our work, which will be discussed by Shomud and I in the next talk. If you have any questions, I think I have finished just in time, 40 minutes.
Questions?
Can I?
Yeah, please.
Am I wrong in thinking that the only extra virtue here is removes the security?
As of now, that is it.
But then I have a question. Normally, at least from my formation, I would imagine that at short distances, not only do you read quantum theory, even space-time is not valid in the normal sense. But this is purely classical
Purely
kind of
classical,
activity.
yeah. Like general
Why
relativity.
should one accept this kind of thing?
Why should we accept it?
Because there is no particular reason.
Why should
to
we
do
accept
it.
Born-Infeld electricity?
No, what I mean is it is only I don't know. That's a different question.
Yeah, that's the question.
That's a different question, but I don't know why. But coming back.
No, as I said right at the beginning, it's not a question of
distances.
it's not a question of acceptance or non-acceptance. Acceptance and non-acceptance will come only through observation. There is no other way where you can talk about non-acceptance.
There's going to be no observation of this in our lifetime and several lifetimes.
That is okay. If it's not that, then we have some job to do. We have some job to do. That's it.
It is an alternate theory which produces probably the same result.
But as I showed you, there are so many alternate theories. So
Yeah.
if you want to, and I said that this is different in some sense because it has a different structure. So if you think that you would like to work with a theory with a different structure, you might as well try and see what happens in this.
So if there were a prediction at the possible large scales
Yeah.
from here,
Yeah.
differs from existing models,
Yeah.
then one can check it.
Yeah, exactly. So what you want
I have
to
not seen anything.
no, what you want to do is you want to find how much this kappa is and whether there are consistent set of scenarios from which you can get a domain over which you can fix that constant kappa.
But a question like gravitational lensing which you are doing.
That we have done, yeah.
So that could be, that's.
Yeah, so we have an exact solution for which we have done gravitational lensing and we have calculated it and
Is
seen.
there a classical area where Einstein's theory produces a result which is different from experiment and you are able to do that, then it will be accepted.
Oh,
If-
that is a, that's
If there is a classical theory,
Which Einstein's theory produces a result
yes,
which is not experimentally correct.
yes.
And your thing produces, then it's okay. Because you are talking mostly at the classical level.
Almost exclusive,
Yeah.
almost exclusive.
At the quantum level or singularity, etc., let's forget it.
Yeah.
So at that level, then the only difference is only
No,
what
the reason for me to do it is that I felt this was something which is not like Brunstick theory, which is not like other theories, which is just moving slightly away from general relativity.
Yes.
But here it is something completely different in structure, and therefore you might as well try and see whether it gives you, like the reason why we coupled both Born-Infeld electrodynamics and Born-Infeld gravity together was to see whether Born-Infeld structure in the matter sector and the gravity sector have mutual influence on each other, and the answer is no, it doesn't.
Sam, one thing is the bound solution generic in the sense that independent of the parameters that you have
No, the solutions depend on the parameter kappa. It will.
No, but do you get similar solutions?
Yes, you get singular solutions. There's nothing like you don't get singular solutions. You get non-singular solutions which satisfy your energy conditions, you would say.
But so there is a parameter range for which you get boundary solution.
No, there is no. For this kappa, there is no range. Is kappa greater than 0 or less than 0? But there is no range.
But oscillatory and this thing, there should be some range.
No, the kappa value is either positive or negative. That is what it is at the moment.
No, but even with a kappa positive, you can have both oscillatory.
You can
and-
have. Yeah, you can have. It depends on the equation of
So
state.
kappa alone is not distinguishing. There is something else.
Yeah, it would depend on the equation of state and price like that.
Your
Yeah.
vacuum solution in this framework.
Is general relativity.
Exactly, so
Exactly.
even all geodetic inertial frame driving.
Everything.
Geodetic,
Goes-
everything works.
is intact. Everything is intact.
Yeah,
No problem.
It's exactly like the torsion.
Yeah.
Everything is a vacuum thing is a
What is it you said?
Okay, so
Torsion is not same as general relativity.
Sorry. I think one of the torsion theories is the vacuum is entirely like general relativity.
No, in torsion, equivalence principle is not respected. In freely falling frame,
I don't know.
The parallel transport will give you a
Yeah.
deficit in the
Yeah.
will go down.
Some
Change will happen.
but since you have a dimensional constant,
Yes.
you should be able to now develop new parameters like Planck length and Planck time.
Exactly. So that is the point that I didn't talk about this, but if you take G, C and this kappa, then you can get natural units. That has been done. But then of course the value of those depends on what is the value of kappa.
Sure, sure.
So that can be done because
Yeah.
you have a dimension of full constant.
okay, so let us thank Sayan. And pass on to the next talk. Yes, by show Jana.